So I'm just opening up the notes from last class. Where we left off last class was talking about the conformations of the sugars and the relative amounts of the different sugars in of furanoses, pyranoses, these different forms and all this stuff going on. And so I said we're going to come back to that after going over the readings that I sent out. Because I think this is something just to start familiarizing ourselves with, which is what we mean when we're talking about the stereochemistry of the sugars. So hopefully this all works. Come on. I don't quite understand what's happening here. Okay. So who actually read the papers or made an effort on reading the paper?
Where did you send the readings?
I sent it by email.
Okay. I either didn't get it or I just overlooked it.
I'll check. Paul, I don't think I sent it to a wrong email address for you. But good job, Ashley. Nope, send it to you. They went out on Friday at 8:28 a.m.
Okay. Well, sorry about that, I guess.
Okay. So the two undergrads both read it. Good for you guys. What I want to go through is kind of work through this kind of the proof, because it's, first of all, it's a really different type of paper to read. It's kind of a history of science, but very technical history of science. And as I said, the original Fischer papers are in German and are basically impossible to interpret, especially with that stupid ass notation they come through. But there's two reasons I like covering this in this course. One is it's early in the course. It provides a little bit of context for where the fields come from. Second thing I think is it's a beautiful example of using logical thought and using chemistry as a platform to do that logical thought. But it's not really about chemistry per se. And finally, it is going to actually talk about some of the kind of chemistry and some of the things we need to keep an eye out for when we're talking about sugars. So the original problem is what he was trying to figure out, what the conformation of glucose was. What is the stereochemical conformation of glucose? And this is at the time, and last class I kept misspelling M.L. Fisher's name because I always do it. So it's Fischer, German style, there's a C in there. And one of the big problems was, what is the It's interesting because it's difficult to think about these things now, just where we are in science. But what is the stereochemical conformation of glucose? And what does stereochemistry mean anyways? Because now we take it for granted that carbon forms, when it's sp3 hybridizes tetrahedral. And like we can actually see that. Like we have crystal structures of things. Like we've actually seen tetrahedral carbon. And of course then that was not known. It wasn't even sort of, I guess it was sort of theoretically conceivable as a way that you could generate two compounds that are absolutely identical in everything but their orientation, that they rotate plane polarized light. And that tetrahedron would be the way to go about doing that, to provide you with two enantiomers that would be identical in every other aspect except how they rotate plane polarized light. But nobody had seen that, and they weren't really sure about this whole tetrahedron thing. And again, no one's seen a proton, no one or knew what a proton was, or an electron, or a neutron. So where we're starting with this is, the problem is that my notes are directly on top of my tablet. I have this giant desk at home, but it's not big enough. It needs to be a bigger desk. So the whole thing kind of came because, again, you have to think about this is very early in chemistry where it's still really unclear that things interconvert between other things and what is the smallest building block out there. But the idea came from the fact that glucose. So I'm going to draw Fischer projections. Again, I promise anyone who, I don't know if any of you guys took my class. Sorry, that should be an aldehyde at the top. I hate Fischer projections, but this is where they're useful. He proposed this, so this is what I'm going to call this kind of like a Fischer projection, where if I don't draw in an atom, it's because it's a hydrogen. So these lines with nothing on them are hydrogen. It'll save us some drawing. So they're not methyl groups, they're hydrogen, so they're kind of a weird new notation, but it's going to just speed things up a little bit. So what he noticed was that glucose and mannose, which had just freshly been isolated from some sort of nut, were closely related. Now, of course, he didn't have these structures that we've drawn here. But what he knew happened is if you took these two molecules and you treated them with hydrazine, phenylhydrazine, which was this brand new reagent, and everyone was really excited about it. I'm not precisely sure why, but any reagent that you could buy from anybody at that point would have been exciting because it was the dawning of the chemical age, and there wasn't like big chemical companies with lots and lots of things in their catalogs. So when a new pure reagent came out, the first thing anybody did was they mixed everything together with it. And they knew that this formed hydrazones. And so what is a hydrazone? A hydrazone is a carbon double bonded to a nitrogen, phenylhydrazones. And what was really exciting about these things is that they make really, really nice crystals. And why is that important? Well, when your only kind of analysis you've got is basically crystallization to common melting point. So you can measure the melting point of crystals, and that's your characterization technique. You don't have IR, you don't have UV, you don't have mass spec, you don't have NMR. All you can do is figure out, are these two crystals the same thing? Then crystals become really, really important. So if you can take things that don't make really good crystals and you can turn them into something that does make really good crystals, that's really, really valuable. And this underlay a lot of the original dye industry, which is how organic chemistry got its start, like basically making dyes for clothes. In the 1800s, and then of course moving rapidly into explosives, and that was a much more, society was a lot more interested in explosives than in dyes. But dyes were the first big money maker that kind of got industry organic chemistry going, and being able to make dyes crystalline made them easier to handle. And so that was really, really important, was you could add these hydrazones onto different things, which were a little bit more difficult, like resins and stuff from plants. And suddenly you can make these kind of crystalline dyes. So it's really exciting. Now, Fischer, of course, was interested in sugars. And he went, well, I think other people had realized that there's an aldehyde on sugars. And we saw that with, I haven't shown, yeah, we saw that with the mutarotation last class. I think it was I have it as slide 4, where we show that we had this open chain version of sugars, and you can go do the 6-member ring and a 5-membered ring, and they flip back and forwards through the open chain. And that open chain has an aldehyde, and it looks like what I've gotten here. So when we take the hydrazone, what we get is we get the same compound for both of these guys. I don't know why it's switching to eraser. Oops. There shouldn't sort of be any kind of nubbin above that. It ends at that double bond. So what we've done here is we've taken the aldehyde at the very top of the molecule, and we've taken that second. Okay, this is really irritating. I don't quite understand why my pen is doing what it's doing. And we take that second OH, and of course when we do that, these are the same molecule, because of course glucose and mannose, if you take a quick look up here, only differ by the orientation of that OH. In all other cases, these things are identical. So this was groundbreaking, because when he observed this, he's like, oh shit, glucose and mannose are related. Like these are close molecules. And we're going to go through the mechanism of how this happens. Of course, they didn't have the mechanism of it, but they knew that you got these adjacent to each other. So how does this work? Well, let's take a simple system. Something like that. So we're not going to worry about anything else. We just have the aldehyde and we have an alcohol, we have an R group. And we add the phenylhydrazone. So this is the reason, one of the reasons we're going to go through this mechanism is if you're completely lost with this mechanism, you might want to review some of the material from an intro organic textbook. And if you can follow along, you're in good shape. So we've got a good nucleophile. We've got a good electrophile in the form of the aldehyde. And so what we can expect to happen is the formation of something like this. Okay. So the most likely thing is, as you all know, and if you need a refresher, carbon doesn't particularly like making two single bonds with a heteroatom like oxygen or nitrogen. And that's what's so weird about the sugars is it's actually quite happy doing that in the pyranose form because of the six-membered ring. But in this case, that's not stable. So it can do one of two things. It can either go back to where we start with the aldehyde, or we can go forward to a slightly more stable molecule. So I'm going to write this as plus minus H plus. So that means I'm going to move an H plus around. And it's mediated by solvent. This doesn't happen directly. You can't, as tempting as it is to use a lone pair on that oxygen to steal the H plus from the nitrogen, you can't do it because it's a four-membered ring, and that's just really, really, really unfavorable. So we get that. So what we've done is we've moved a hydrogen around, and then we can kind of kick out water. Well, it's not really kind of. We kick out water, and we generate our hydrosome. But this is only a monohydrosone, and we get these dihydrosones from this system. So what's going on there? Well, this is where it does get a little bit tricky. So let's think about this molecule here. If we have a little bit of acid present, you can imagine this can become protonated. So I'm just going to note that here. So I don't need to redraw the molecule to just add an H plus. So we can have that. Now, if you remember a lot of the second year and definitely in third year chemistry, a lot of what this was about that. This system here is going to be in equilibrium. You know, you can have solvent, but let's just keep using phenylhydrazone for everything because why not? With the enamine, it's kind of like an enol, but for nitrogen. So you have a system like that. Nothing wrong with that. It's feasible. You could argue that in a neutral molecule, this is enamines are slightly more stable than standard kind of enols. So these are more favorable. Having a double bond nitrogen going to this double bond carbon is more favorable than having a double bond carbonyl like an aldehyde going to the same version with an alcohol. But it's not necessarily the most stable thing in the world. And so this, of course, one way to draw this is we can consider that, oh shit, this is now an enol over here. If you choose not to use the profanity, that's also okay and fully acceptable. Okay, so now we have something like this. It makes sense. We kind of just moved the double bond around, right? We've tautomerized this molecule. Nothing wrong with that. Now we have an aldehyde, or well, I guess it's not an aldehyde, I guess it's a ketone. But that ketone is now set up like the aldehyde we had at the very beginning of this whole thing. And so one can imagine that another equivalent of the hydrazone, because this just stuff keeps on coming. Remember, it's the new magic reagent that your buddy Friedrich just sent you from Berlin. He's all real excited about it because he's able to crystallize indigo. So you just dump it into your sugar willy-nilly. The other thing that's always fun to look at in these old papers is the scale that people did the kind of chemistry on. Today, we'd poke ahead on 100 milligram scale and think that's quite a lot of material. At that time, they'd poke ahead on, a few kilograms and think, oh, I'm not sure that's enough. But when everything you do involves crystallizing, you do need to work with quite a lot of material. So attack, do this whole hemiaminal resolving H plus changing thing, and we'll end up with double bond. So kind of telescope these first 4 steps. Here I haven't drawn them all out. So I want to make sure I do this right. What have I screwed up? I've eliminated carbon for no particular reason, which is a problem. But as you can see, we clearly don't have a double hydrazone. We've got a hydrazine on one side and a hydrazone on the other. And that's not where we're going to go. So I need to reduce this other guy. And I am going to temporarily cheat, and I'm going to get back to you next class because I have made a mistake. So I'm just going to write, I am oxidizing this, and will go to the double bond, but I'm obviously missing something. I just can't remember what. And it's not jumping to me because I am close to the board, so I'm obviously a moron, because the closer you are to drawing anything, the stupider you get. Okay. But this is that double hydrazone that we saw on the previous slide. Of course, you're not responsible for this mechanism, but this is kind of how we're making these kinds of systems and how these things arise from adding this thing is all that enol ketone tautomerization. And so it's a good thing to be aware of. If you can't follow that kind of chemistry, then please go back and review it. Okay, so what we know then is mannose and glucose make the same molecule when you do that. The other big thing that was happening about the same time, which was kind of cool, is there was a molecule called Arabinose, which was another easy sugar to get from. I think you isolate it from Brussels sprouts. And if there's one thing that Central Europe has a lot of, it's Brussels sprouts. So again, we're cheating here because we know what the final structures of these molecules were, whereas at the time he didn't. So one thing to jump at you is this is not a hexose. So a hexose is what we've been working with: glucose, mannose, galactose. Hexose, there's 6 of these hydrates of carbon. This is a pentose. There's 5 of them. There's only 5 carbons. So in the paper, I was talking about this, and this is one of the first really cool, and it is stereoselective synthesis, is the chain extension of these systems using hydrogen cyanide. So if you take Arabinose and you have a death wish and you treat that with hydrogen cyanide, which is absolutely freaking insane, and no one in her right mind would do this. It's really amazing that any chemist in the 19th century lived at all. Like, they got their graduate students and undergraduate students would have been in the lab doing these kinds of reactions and occasionally getting hydrogen cyanide poisoning without very good ventilation. The more you think about it, the crazier it is. So, have I drawn Arabinose wrong? I drew Arabinose right. So the major product coming out of this so it's clear, is that where this new OH group is syn to the one below it. So you take that molecule, and this is chemistry that is safe to perform, unlike anything we've seen so far. But don't worry, we're going to get back to stupid chemistry very quickly. So if we take acid and water, at that time they would have used sulfuric acid. Today we would use sulfuric acid. So some things haven't changed. It's actually one of the depressing things that keeps getting pointed out to chemists by people in biology and physics, is that fundamentally, if you actually look at some of the pictures in that paper, I can call it up just for a second, because I always find this absolutely ridiculous, but it's just, chemistry is weird. Let me just find the right picture. There it is. So I'm going to just stop sharing for a second. I'm going to share on this picture. So this is like a lab group photo from, 1878. It's the Bayer lab group at the University of Munich. This thing behind them there is a fume hood. There's a little fume hood off here to the right. and there's a little desk underneath it. And they definitely dressed better than graduate students do today, or than PIs do today. They all wore their suits in the lab. Most of these suits were made of cotton and wool, and that was actually kind of intentional. It gave them more protection because it took a long time for anything to get through it. And they also were kind of fire retardant because it does sort of hurt to burn. But you can sort of see, like, up here, that's a round bottom flask with a filter in it. That basically looks like exactly the same type of equipment that we have today. Like, we are doing chemistry in round bottom flasks with, and we use funnels like this to pour shit into them. There's kind of a low resolution alembic over here, and maybe our distillation apparatuses look a little bit different than this. But fundamentally, we could bring one of these dudes into, and they are all dudes, into a modern chemistry lab, and they wouldn't be completely lost, though they probably would question why we need all this ventilation. So it's really unusual, these fume hoods, this whole thing. So way back then, this is a large lab team all doing this kind of chemistry together. And nothing's really changed, except there are thankfully an expansion of things from just lots and lots of white men to groups that aren't entirely white men. There's still too many white men. Okay. I guess not too many white men, but too few non-white men. Where are my controllers? There they are. Says a white man.
That crooked fume hood was really bothering me in that picture.
I think, yeah, I'm sorry. Installation teams haven't gotten any better either.
Damn contractors.
Yeah, contractors are the same. So if we go back to this, you treat cyanide with acid and water, and you hydrolyze the cyanide. It's already at the acid oxidation state, of course, because it's triple bonded to nitrogen, and you get the acid up here. Now, of course, what we've done is 1, 2, 3, 4, 5, 6. So we've converted a pentose into a hexose. And what was noted was, if you take this thing and you treat it with red phosphorus, I don't quite know what you've done to phosphorus to make it red. I do know that it catches fire basically with everything. It's a little bit more stable than white phosphorus, which gets used in like munitions today and is banned under almost all the rules because it burns and burns and burns and nothing can stop it burning. Red phosphorus isn't quite as burny, but still pretty reducing, because what it's going to do is strip away all the alcohols and give us hexanoic acid. And so this is kind of how one of the ways they found out that all these sugars had 6 carbons was because they treated them with red phosphorus and they got hexanoic acid for all the different sugars. I'm not going to draw in all the carbons there. The carbons haven't done anything. It's just we've ripped away every single hydroxyl group. Okay, so what we're going to call this thing is we're going to look at this and we're going to pull back a couple of slides. And so what we can see is right, 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 left, left. Okay? Right, 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 left, left for mannose. So when you take mannose, and of course, remember, Fischer has just isolated mannose from some nut. So he's like the dude with the brand new thing. So he's got something that no one else has got. And again, nothing's changed. People still do this, right? When they've got something new, they exploit it before their competition's able to get it. So he took this and he oxidized it. At the time, oxidation was done through things like bromine oxidations. This works a lot like chromic like the Jones reagent, actually, if you want to try and draw a mechanism. I'm not going to right now because of time. But you're going to oxidize the aldehyde up to an acid without touching the alcohols. Well, that's interesting. Those two things are the same thing, right? So we're going to call this. I always get the names wrong for these things. Manoic acid. Then we can oxidize this further by treating this with. I'm sorry about my crooked arrow there, Paul. I know it must be bothering you. So we're going to oxidize that using acid and nitric acid. Unsurprisingly, it's going to oxidize something. It basically takes the terminal alcohol up to a carboxylic acid. Manoic acid, because of course it is. It's a stupid name, but we'll keep track of that. Okay. So, question then becomes, manoic acid is an interesting molecule. No, it isn't. I always get confused at this point. So we'll come back to that. So this is some information he had. The next thing that had just been discovered, because this was a time of discovery, was Xylose had just been uncovered. And Xylose is again another pentose. Xylose had been isolated from wood waste. People got really excited about isolating sugars from basically everything. And one thing that was noticed was, again, I'm going to just show the reagents they used at the time. Sodium and mercury. Not the least bit explosive and dangerous. Of course, it's explosive and dangerous. It's absolutely insane. But this was in times before sodium borohydride. And so when they do that, you reduce the aldehyde down to an alcohol. This is xylose. The fully reduced forms of sugars are called etols. So xylitol, mannitol, glucatol. And what we have here is we have a meso compound. Right, so remember what a meso compound is. It's a molecule with an internal plane of symmetry. There's a plane of symmetry right there. The molecule basically is its own mirror image. So if we take the mirror image of xylitol, it's been a little while for you. I'll do this. Draw the mirror image. That's theoretically the enantiomer, but you take this thing, and the one thing you're allowed to do with Fischer projections, the only thing you're allowed to do in terms of rotation is 180-degree rotation. And if we do that, they are the same molecule. So xylitol was meso. How did he know it was meso? Well, when he tried to measure the optical rotation of this by sticking it in his polarimeter and looking at how it rotated plane polarized light, he found out it didn't. Okay, so we have xylitol. We know xylitol is meso. But this being the era when we know that we can take pentoses and turn them into hexoses, because we just saw that with Arabinose, well, let's treat this with hydrogen cyanide. Because why not? And again, what we're going to do is we're going to have those two OHs line up syn to each other because that's the preferred stereochemistry. Again, this is the first stereoselective reaction that was ever done where you're actually taking a non-stereo center and you're turning it into a stereo center. And you're preferring one stereo center over another, and your eraser keeps erasing everything you draw. Now we take that and we whack it with acid and water. And we hydrolyze. And now we get a new molecule. And now what he did, of course, the first thing he says, like, okay, great, I've got a new acid. It's a hexose. Let's go try and crystallize it with everything and see if it's the same thing as anything else, and it wasn't. So Xylose didn't seem to be the same thing as anything else. So dejected, he acidified it again. I don't know if he was dejected. Probably not. I don't think he was ever dejected. His grad students might have been dejected. You know, this was a time when you could get a PhD thesis by crystallizing a molecule. Now we expect you to do that in an afternoon. It's unfair. And we make this molecule here. Okay. Now, again, he's looking at these because what we've done is we've made a few of these diacids already. And so the one I'm going to pull out is, let's take a look at, again, our good old friend glucose. Okay, I'm going to try my other pen, see if it doesn't erase things randomly. 1, 2, 3, 4, 5, 6. Okay, it's 6. So this is glucose again. Oh, this is better. It's not but it's not drawing properly. Okay, I'm going to switch the battery in it. I'm going to try and install it upside down first. I don't think that's any better. Okay, that's worse than things erasing themselves for no reason. So if we take glucose and we just oxidize the crap out of it, so we do a double oxidation, first with bromine, then with the other thing. Sigh. Okay, I'm going to just have to live with erasers. Yay, technology.
It could be PowerPoint. I find that it's kind of a bit wonky with the stylus.
Yeah, it probably is. I can switch to EndNote. The problem I have with EndNote is whenever I try and create PDFs from that, it splits my like a structure right down the middle. So this way, I switched to last class. I was coming up with the notes. I thought, man, these look really crowded. And I'm kind of circling back on myself. I wish I had more space. And I realized that I could just change the slide shape to an 8.5 by 11, and then it's like a printable page, and it's exactly writing on a page. And I felt like a moron for never having realized that in all the years of doing this, but that was an option.
I didn't even realize that was an option, to be honest.
Well, I make figures like this all the time. It's just I never thought about doing it on that. So it's a much better shape for writing this because it's how my brain thinks about a page at a time. And so trying to fit it onto this makes a lot better than working it onto that landscape PowerPoint slide. Anyway, um, so the nice thing is that these will now the notes will be like one page each kind of thing, like one PDF, and just they fit beautifully on 8.5 by 11. We're probably a little bit zoomed in. Everything's gonna be ginormous, but still, whatever. You're probably not gonna print them. Um, so anyways, we have got a carboxylic acid now, dicarboxylic acid. And now if we can, so then again, using the stupid naming system that we've developed, this is glucaric acid. If it only has the one carboxylic acid at the top, it's gluconic acid. But because we've got two carboxylic acids, it's glucaric acid. And no, you do not need to know the names of these stupid acids or things. It's really not relevant. But I just want to make sure that I am actually writing down the right names. And this is supposed to be glucose, not whatever the hell that was. Okay, so now if we compare glucaric acid to whatever the hell this thing is, what's the relationship between those two molecules?
They're both derivatives of glucose, or sorry, never mind. I was confusing which
What's
two you
their
were talking about.
isomeric? Are they the same molecule? Are they diastereomers? Are they enantiomers?
Um, they'd be distereomers, right?
Yes, but they're not. So the one thing you're allowed to do with the Fischer projection is rotate 180 degrees. So let's do that with this guy. So the top becomes the bottom and the bottom becomes the top. And then all the lefts will become right and all the rights will become left. So this guy is that guy, this guy is that guy, this guy is this guy, this guy is this guy. So the confusing thing when we do this oxidation is we kind of lose track of the top and bottom of these molecules because normally the top is the aldehyde, the most oxidized state. That's what you put at the top of the Fischer projection. But now you got acids on both ends. Okay, now it might be easier. What's the relationship between these two molecules?
Are they enantiomers?
Yes, they are. And I'm going to say somebody other than Paul next time. Paul's doing a great job. They are enantiomers, right? So this is glucaric acid. And because of it was rotating right to the right, it was called D-glucaric acid for dextrorotatory glucaric acid. And this was called L-glucaric acid. This was the first time they assigned the D and L to anything because it was levorotatory. And because this came from glucose, this got called D-glucose. And I think glucose was dextrorotatory, but that's not necessarily true for any of the other sugars that are D. Some of them are not dextrorotatory. They do not rotate light clockwise. Some of them rotate light counterclockwise because we still do not understand why light rotates the way it does for given enantiomers. There's no model for that. It is not a solved problem. We can't predict the way that things are going to rotate light, which is actually a really, really cool thing when you think about it. That should be predictable. It's simple physics, but really, simple physics is really complex. Okay. So, what that told us is that from xylose, when we do this hydrocyanation, we get and then dioxidize, we get the enantiomer of glucose. But we know that, yeah, so we have that information. And we know that xylose itself, if we reduce it down, makes a meso compound. So this was really all the information that he had to try and figure out what the stereochemistry of these guys was. So I think the paper takes us through this really, really well from here. So if you have a second screen, that's useful. If you don't, I will walk through it here, and you can sort of confirm this later. And what the paper I sent you does is basically it takes Fischer's original paper and almost reproduces it word for word while translating into English and cleaning up the language a little bit. So what he did was he followed glucose, mannose, and arabinose in parallel. So if we do that, and we can do that. So arabinose, and he's starting with the aldehyde. So we know that there's an aldehyde up top. You know what? I'm going to just make sure they all line up. So arabinose needs to end before the top. And we know these are all related sugars. So he just arbitrarily stuck the first chiral center to the right. That was pure fucking luck. People say it was luck that he stuck it to the right. And if he had stuck it to the left, he would have been drawing the enantiomers of glucose. I disagree, in that we define Fischer projections the way we do because it's correct, but we could have actually flipped how we look at Fischer projections, and then it would have been still correct. Because we say, okay, the left and right things are coming out towards us, the back and top are going away from us. But if we had actually switched that, then it would be correct. So I don't think it was so much luck as we've kind of gone back and re-engineered everything to make sure it works. But, that's not as good a story as saying that he was right. And mannose. So we know that. So what do we know about these molecules? Well, we know that when we reduce the arabinoic acid, like the acid version of the arabose, it's not meso. Whereas the xylose was, the arabinose isn't. And so if this top OH was to the right, then we would basically inherently have an internal mirror image within the molecule, because it wouldn't matter which way that middle OH went. It would be an internal mirror image. Right? So if you draw this to the right, then if this was to the left and you had the acids on both ends, these guys, you could flip these two stereocenters with each other. You'd have an internal mirror image right through the middle. And if it was to the right, you'd also have an internal mirror image. So it wouldn't matter what was happening with the middle one. So we know that in arabinose, the top one must be to the left. We don't know what's happening to the middle here. We don't know if it's left or right yet, but we know that if the top one was to the right, we would have an internal mirror image. And we know that the arabinose version and mannose, that OH is consistent in both. Because remember, for Arabinose, we were able to take Arabinose and we were able to turn it into the same thing as minoic acid. So we were able to convert Arabinose to minoic acid. So mannose and Arabinose have to have the same orientation, and we know that glucose and mannose have the same orientation at that point, because we know that when we make the phenylhydrozones of glucose and mannose, we get the same molecule, and the only thing that changes there is this top OH. So those have to be opposite each other in glucose and mannose. So far, so good. So in red, Arabinose is not meso. Must be not same as bottom. 2. Arabinose can be Arabinose roughly equals mannose. And 3, glucose and mannose share same configuration at carbon 3. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So carbon 5 we assigned arbitrarily. Carbon 3 we can solve what it is because we know that Arabinose is not meso. And that leaves us with carbon 2 and carbon 4 that we don't know the stereochemistry of. And, in Arabinose, there's only one left. In glucose and mannose, we've got a bunch more, right? We still have 2. Okay. So, the next thing that we followed was the idea that, well, shit. We know that I always need to make sure I'm following this correctly. Glucose and mannose have to have the opposite, and we know that mannose is optically active. So if mannose had the OH, need to make sure I get this to the right here, like that, and the acid is optically acid. Both acids are optically active. So if mannose had this OH to the right, I'm going to actually change color. Let's just think about this for a second. Then glucose would have to have this to the left because we know they differ at that point. But we know they have to be the same at this point here. So if they're the same here, that's to the right. One option is to put this to the left, like that. We're going to be erasing this in a second. Now the problem comes, if you oxidize both the top and bottom carbons here, this is no longer optically active. Because right, left, draw the mirror image of that, it's superimposable on itself. Because you can rotate that 180 degrees and it'll be superimposable on itself. So that doesn't work. Okay, so this can't be correct. Okay, now what if, okay, so that's wrong. Fine, that's okay. We're not screwed yet. Let's put the OH on the right down there. Okay, glucose needs to do the same. Okay, now look at glucose. If I oxidize this up and this up to the carboxylic acids, I'm equally fucked. because now I'm right, left, left, right, right, draw the mirror image of it, and suddenly the mirror image of this guy is no longer optically active. The mirror image of this guy is the same thing. It's its own self once you have the carboxylic acids on both ends. So what that tells us is we've made a mistake with this top thing here. This is impossible, because if mannose is that right compound, then there's no way we can put the other carbon in place and have both the mannoric acid and the glucaric acid optically active. One or the other is not going to be optically active, no matter what we do with that other carbon. So the error must have been made up here. So mannose must have this to the right. Glucose must have this. Sorry, to the left. Glucose must have that to the right. I guess then I probably said then's the wrong word. No matter what you do at C5, one of them is not asymmetric. Um, or one of them is meso. That's probably better. So it's kind of this is I think to me the most beautiful part of this entire proof. It's basically thinking through symmetry. And why I really like this is when you're thinking about making a molecule, any kind of molecule, no matter what, symmetry is your friend, and you should always be trying to think about how to carry symmetry as long as possible, and then how to strategically break symmetry. And it's this beautiful hypothetical logical step that we just did, which is not obvious if you don't know to look for it, and you don't have all these pieces of data about the different acids being the same thing or different. Um, you'll never see it, and if you haven't collected the experimental data, you'll never see it. But then once you've done that and you sit down and think about this logically as sort of binary choices on what to make, on how to arrange these, you eliminate one of the options because both the other ones lead to meso compounds, and it's just brilliant. Okay, so at this point we've assigned all of the centers except the last one down here. And the way we assign that one is done on the idea that glucaric acid has an enantiomer, which is the gularic acid that we just did. So what we know is that there must be an internal plane of symmetry within glucose. The possibility of that, sorry, you have to be able to make the enantiomer of glucose. And so if we go back to what gularic acid is, remember we have this thing where this guy, the glucaric acid, which is derived from the gulose, which would be the sugar if this was an aldehyde. And the reason he found that is he literally said, I switched the U and the L and dropped the C. So it's glucose, but just gulose. And I wish he hadn't done that. I wish it had been called anything else because it's really hopelessly confusing. But we know that when we oxidize it, it makes the enantiomer of glucaric acid. So what that tells us is we need to be able to make it so that we can get that enantiomer. And I always do this wrong. Yes, because that's why I'm confusing myself, because there's a little nubbin at the end there and I'm driving myself nuts. And the only way that's possible that you have the enantiomer of that is if that one's to the right, which means that the mannose has to be 2. So glucose and glucose have to be head to tail and anomers of each other. So at that point, we've assigned all of the stereocenters of glucose, mannose, and arabinose, because arabinose is based on those guys and it follows. And so we satisfy all these conditions of things being, when they're supposed to be optically active, are optically active. When they're not supposed to be optically active, I'm just going to change the color there. So how does that green one work? Okay, so the green one we have to remember is glucose comes from xylitol, from Xylose. We know that xylitol is meso. Now, we also know that glucose is the head to tail enantiomer of glucose. And glucose comes from L-xylose. Like, if we go back there, we take a look. Sorry, no, I'm confused. No, it's D-xylose. I'm just a moron. That's all. So, if we think about what that center has to be, and we can work through it, how much time do we have? We've got 10 minutes. You know what? I'm actually going to leave that as an exercise. Like, that's the clue of how to work through this. Is glucose comes from xylose. Xylitol is meso. That means glucose has to be the head to tail enantiomer of glucose. And so if you take a look at glucose and you try and assign that to the other side, you'll see that that will fail. I'm going to leave that as an exercise. We'll take that up next class. It's been a while since I've worked that out, and I don't seem to have the notes in front of me. So I'm going to be completely open and saying that I'm going to kind of stumble around trying to draw that out. But let's all try and work on that, and we'll take it up next class. I'll call on somebody to give their solution for that. So at that point, Fischer was able to assign that. The paper finishes that we have here with the assignment of all the different sugars. And at that point, some of those sugars were prophetic. They had never been seen before. They'd never been identified. But we went, okay, well, this is how this works. We've got 16 different ones. I expect to see 16 different sugars. Because then you have the D of each of them and the L of each of them. So we're not going to see a lot more Fischer projections in this class, thank God. I do really, really hate them. But they're really useful for these proofs.
So sorry, the exercise that you want us to do is to work out
Proof
why the
5.
C4 can't be the other way?
Yes.
Okay. From that, okay.
Proof 5. So the knowledge you need there is there. I actually need to sit out with all these things in front of me and start drawing things out. But really, it comes down to the idea that the xylitol is meso. And so there's only one way that can be the case. It really needs to be that way, because if it's not that way, then it's not meso. Okay. Okay. I think so. The last thing I really do want to touch on here is okay. We talked about the alpha and beta thing, so we've covered that. We've talked about meter rotation. We covered that. Talked about that. So I think I just want to talk about some of these sugars, and just so we can get an idea of the structures of some of the sugars that we're going to be seeing a lot of in the class. Because most of the time we're not going to draw them with the fish projections. We're going to be just drawing them with the chairs. If it's been a while since you've drawn some chairs, practice drawing chairs. So remember, again, this is the anomeric center. It's a mixture of alpha and beta. The alpha is when this is axial for almost all these sugars, and that's because the stereochemistry at this position is such that these match each other if this is axial. So in glucose, everything is equatorial. So what we would call this one, let's say I'm going to draw, oops, did I just erase everything? No, I didn't. I'm going to draw one enantiomer, or one anomer, sorry. I'm going to draw the beta. So we would call this beta D, D because it's D-glucose, glucopyranose. So in this name, I've got all the information about what exactly is here. It's a beta glucoside because this thing is equatorial. It is D that tells me the enantiomer. It's kind of like R and S for the entire molecule. It is glucose that tells me the relative stereochemistry of all the hydroxyl groups. And it is a pyranose, which tells me it's in the six-membered ring form. The other big ones we're going to see are galactose. So this would be alpha D galactopyranose. It's arbitrary that I draw an alpha instead of a beta. So note what we've done there is we've taken the C4 hydroxyl and it has gone axial. You are going to hate mannose by the end of this class because it is a freaking irritating molecule. This is beta D nanopyranose. So again, everything's open book, so you don't need to memorize these. When people need to memorize these, you used to remember mannose was when you turn the nose. So the topmost hydroxyl group is the opposite of glucose. And galactopyranose is when you turn the toes. So the bottom most OH is flipped. I would say that those are our major compounds that we are going to be discussing. The one thing I really want to talk about is how we flip between these. We kind of sketched over that. We didn't talk a lot of detail about how we interconvert between the different molecules. So let's just draw a mechanism for that. The open and closed chains, I guess. So let's use glucose. Let's do this under acid. I want you to try it under base as well. Again, try this as an exercise. It is an assignment question, which means it's a potential exam question. So you protonate. Then what happens is we are going to help this guy out. We want that to leave. And the way we make it leave is by the we could have that leave directly and form an oxocarbenium, kind of like an SN1 mechanism, but that's not generally what happens. What generally happens is now this thing undergoes a ring flip. So again, if you need a reminder on how best to draw these, the best way to do a ring flip is slide every atom over one atom. Well, this is my best way to do a ring flip. Slide everything over one position. So the C6 is now axial instead of equatorial, and it's still up. The C4 here, if it doesn't erase itself, is now axial instead of equatorial. The C3 is axial instead of, it's glucose, so everything's axial. And the C1 is also axial. So what I want to do is I want to zoom in on this site over here. So what we see there is we have the oxygen and we have the OH. And it's protonated. So it's a really good leaving group. Now, let's just think about this bond. Let's think about where the lone pairs are on this oxygen. Well, one lone pair is going to be out here. And one lone pair is going to kind of be back into the page there to make the tetrahedron with the rest of the chair. So if you have a model kit and you want to build your model of that, just instead of using one, just make sure your oxygen is tetrahedral and the things with nothing attached to them are where your lone pairs are. So this lone pair here is now directly aligned with the antibonding orbital of this OH bond. So if we think about that, we've got a bonding orbital, this is the sigma bond, but there's also a sigma star, which is the antibonding. So another way to draw what we have there is we could draw it using a linear combination of atomic orbitals. Sort of pseudo. We're not going to need to draw them all. Let's just worry about the one that we're interested in. That's the sigma. There's an electron in each of those, right? The sigma star, this is going to be the weakest bond in the entire molecule because holy shit, there's no H2 leaving group there. That looks like a good leaving group. That's going to be a bond that's ready to break. So it's got to make it a weak bond. So the sigma star, I should draw this on top because it's higher in energy. I just don't have room, so I'm drawing it off to the left. But don't worry, we're going to draw a lot more of these. Or maybe worry, we're going to draw a lot more of these. Depends what you think about orbitals. I like orbitals. Is we have the antibonding orbital of an sp of a sigma bond made by two sp3s. And what that is, of course, is you have the lobes inverted. So the major density, there's no electrons in it. It's an empty orbital. But the major probability of being able to accept an electron is opposite, being in between the two atoms. And of course, this lobe here and that lobe here are perfectly aligned. And so the lone pair from this oxygen can donate into this guy. And when we occupy that, when we're using electrons and we're filling the sigma star, which is what we're doing, we're breaking the sigma bond. Because whenever you occupy a sigma star bond, you break the sigma bond. That's a sigma star orbital, you break the sigma bond that's associated with it. And that's going to start looking an awful lot like a pi bond, and that's what we get. So mechanistically, I'm not going to draw the stereochemistry of all the other centers. We're just going to worry about this guy for now. We're kicking this bond out through sort of an anti-periplanar elimination, almost as like an E2 elimination, if you remember that. The electrons are lined up anti-periplanar to that CO bond. It's just they're not coming from a bond, they're coming from a lone pair, but the geometry is the same. It's the same as an anti-periplanar E2 elimination. And what that will give us is a new double bond. Note that I'm actually changing the conformation of the ring because six-membered rings, chairs don't exist when there are two sp2 centers in a molecule. We'll talk more about that and about the conformations that those things arrange. What this is called an oxocarbenium ion. we are going to see an awful lot of them. They are like the most important intermediate in sugar chemistry. This is in equilibrium, or well, I guess it's in resonance with the carbon. So that's why it's oxocarbenium, because the positive charge is on the oxygen and on the carbon. So it's a carbenium ion, but it's an oxocarbenium ion because the oxygen participates and stabilizes the charge. It's quite it's quite a stable kind of thing. It can exist, and most of the chemistry of glycosylation is figuring out ways to selectively make oxocarbeniums and selectively react oxocarbeniums without having them go crazy and just do crazy stuff because they're still C plus, so it's going to do chemistry, um, or have them happen when you don't want them to. Okay, it's 5:21. We're going to leave it there for today. I haven't posted the YouTube video from the last one. I haven't posted the notes. I'll try and get on that probably first thing tomorrow morning before I do anything else. But my brain's probably as fried as yours. So I think we're going to call it a day unless there's any other questions. Going once, going twice. Thank God. Okay.